Hey everybody, welcome to another CS302 assignment. This one's going to be implementing this crane program. So I have this silly paragraph right here, but here's how we can visualize this program. So obviously when we have our binary tree memory, it won't look quite like this, but this is a good way of visualizing this problem. So we have a crane. We want to be able to lift up a set of objects and put it somewhere else, which I guess that's what a crane naturally does, I suppose. So this is also going to be another one of our, it's another ACM competitive coding problem. So we essentially have a set of nodes. Each node in our binary tree could either be a joint, which a joint just connects between two entities, which could be also joints or objects. So this is a simple version where we have the root node's a joint. Then we have these two joints right here. And then this joint has on the left side, on its left arm, a car. The right arm has a bike. Left arm has a bike. And right arm has a car. Now these numbers right here are going to denote the respective weights of each object. So it's not really accurate because I think cars are heavier than bikes, but just go with it for right now. So in this case, we have different weights, and then we have different arm lengths. And we want to only be able to, we only can lift this structure up safely as long as everything balances out. So in this case right here, we have a car and a bike. So for this joint, if I take the arm length, which is 2 multiplied by the weight of the car, 5, we have a torque of 10. On the right side, we have a bike, weight of 10, weight is 10, and the right arm length is 1, so 1 times 10 is 10, so the torque on the right side is 10, and the left side is also 10. So therefore, it's balanced on this side. Now the right side, for this joint, the left side, the bike has a weight of 3, and the left arm length is 4, so the torque will be 12 on the left side. The right side has arm length of 1, and that car weight will be 12, so 1 times 12 is 12. So for this joint, the left and right side has the same torque of 12, so it's all balanced out. Now, each joint, we can imagine, has no real weight. So the weight of the joint will be the combined weight of the left and right side. So essentially, this joint weight, if you want to call it that, has a weight of 15 because the left side has a weight of 5, the right side is 10, so the 15 will be the weight right here. And for that joint, its weight is going to be just a sum of the two weights attached to it. So this joint, its weight will be 3 plus 12, so 15. So these two joints have the same weight of 15. And then for this top joint, the left side torque is 2 multiplied by the weight 15, so 30. The right side length is going to be also 2 multiplied by 15 is also 30. So at the topmost joint, the torque balances out, and there's no more further nodes in this tree, so everything is nice and balanced, and the crane is able to successfully lift this without causing any danger. So that's going to be sort of the idea of this program. So I think conceptually it's not anything too complicated, but again, now we have to code this, which of course is going to cause some complications. So let's go ahead and now discuss our classes we're going to use to store this structure. Okay, so here's our binary tree classes.h file, which is going to be provided for you. And in this file, we have several classes, and they will all be implemented for you. And the reason why is because they're all a bunch, every function in this class is all just a bunch of getters and setters, and they're one-line functions. So really, there's just not much to do. So I mean, you could implement it yourself, but really they're so basic, it's just why waste time with that. So we have this bintree node class, and it's going to almost be a little bit like an abstract class, but it won't be abstract because we don't have a pure virtual function. We have our virtual function getWeight right here. So this is going to be our parent class because we're going to have several different nodes in our binary tree, we want to be able to navigate them and then call each object's get weight function and so forth. So because we have different objects, they have different ways of computing their respective weights. So we have our private members left and right. Now, in reality, we don't have to make them private because I actually do have these two getters, get left and get right, which returns left and right anyway. So there's no point doing that, but I guess it looks fancier to have a public member to retrieve them. So why not, I guess. And then we have an arm length variable, which we can, of course, can get and set the arm length. So very straightforward. We also can set the left and set the right child pointers as well. So really very basic class. And this vertical function is needed because we're going to traverse our binary tree and then we hit certain leaf nodes. So essentially, these nodes right here are going to be our joint nodes. So any of these joints will be our bin tree node. And then our non-joint nodes, the leaf nodes, will be car, bike, and go-ped. And as we traverse our tree, we don't really know what the objects actually are. So upcasting is going to be the only way to be able to correctly, accurately retrieve the correct weight of each object. So now we inherit bin tree node into go-ped. We can see here, very basic. We just simply set the go-ped object using the constructor, and then here's the weight function. So we have these three fields: the wheel weight, engine weight, tank weight, and this is going to be a way of computing our weight. So we can see here, if you have a bin tree node pointer that points to a go-ped object, and I call get weight using that upcasting technique, it will call the go-ped's get weight function. Then, of course, you have our bike object, same idea. You have separate set of fields. We have our constructor that sets those two fields accordingly. The get weight function uses this formula to compute the weight. And then for our car, same idea. We have several fields. Our constructor will set these. This is going to be our method of returning the weight. And of course, you have these private members right there. So nothing too fancy. And then in the PDF, you can see here, here's how you would, of course, set this up. So you can have our pointer PTR. You can set equal to a new bike object. And of course, this is going to allocate a bike object to the pointer. I say get weight. So PTR is of type bin tree node. And of course, right here, upcasting will happen and it will call the bike's get weight function. And likewise, right here, if I say PTR equals new go-ped, pass in the fields. If I say PTR get weight, PTR is an abstract-ish class, it will call the go-ped's get weight function. So that's going to be the idea. Now, what we have to do, essentially, is we also have to somehow find a way to store the arm lengths for each object. Now, of course, these leaf nodes don't have any arms, but we have to store the arm lengths in each of these leaf nodes correctly. Otherwise, this is kind of going to be tricky to implement. So right here for this node, this is going to be our bin tree node joint. So we can store the value 2 into this car's arm length. And we can store 1 into this object, this bike object's arm length. So that way, if we store that 2 in here, the parent node will be able to easily extract and retrieve the weight of these two leaves, and it will be able to also get the arm lengths as well. So looking at this, well, if you look at this node right here, if I call this node's get left, it retrieves this object, and of course then I can call this object's set arm length, get weight, and so forth. So we're going to store the arm lengths in the actual leaf nodes, and store them in the actual children node. So for example, even this parent node, we have to store the arm length into these two joints, 2 and 2 in here. So we have to be able, so that's kind of the workaround to make this work. So again, I'm not going to code that part for you, but just think about this. So you want to store these weights or store these fields, by using this constructor to allocate the object, and we have to store the arms. So using the parent node, we have to store the arm lengths into the children nodes accordingly. So again, that's all. I'll leave it at that, but hopefully this gave you a little bit of an idea as you work the assignment. So now what I'll do is I'll cover the main portion. So I'll talk about a little bit as to how to interpret the input file and some tips as to how to build the input file and give you some ideas for how you would build the how to write the recursive function that will recursively traverse this tree and determine if this structure torque-wise is balanced or unbalanced. Okay, so your input is going to essentially look like something like this, for example. So each line will contain either the word joint or some object name. This one's a very simple example, so I'm going to go to actually Crane 2 for a second. So here's an example of a typical input file you can expect. So each line is going to contain first either the word joint or it'll contain an object name, so bike, GoPed, or car. And if you read the word joint, then you're going to have two numbers on that line, one for the left arm, one for the right arm length, and same thing for each of these joints. And then if you have a bike, well, you're going to read in these two additional values. So let me just look in this, for example. I forgot the actual fields. So for a bike, you have a wheel weight and a frame weight. So basically, 1.5 would be the wheel weight, and 2.0 would be the frame weight. So you just simply read in those numbers, and then you pass these two values into the bike constructor to allocate the bike object. Then for the GoPed, right here, so for GoPed, you have these three fields. So if you read the word GoPed, you can expect three numbers to be on this line. And it's going to be essentially the wheel weight, engine weight, and tank weight in that order. So you read in these three numbers, and you pass those three into the GoPed constructor to allocate the GoPed object. If the line that you read contains the string car, well, you can expect to have four fields or four numbers afterwards. So for the car object, we have wheel weight, engine weight, transmission weight, and body weight. So those four will be in that order. So you read them in that order, and you pass it into the constructor. So the constructor is kind of one-to-one with these private members for each object. So the input will be nicely formatted. So essentially, you can see here, you can use the input operator, the extraction operator, because everything will be space separated. So of course, you can first read in a string, and based on the string read, you can expect to see the correct amount of elements on that line. So if you see the word joint, you can expect two integers. If you read the word bike, you can expect two doubles. If you read the word GoPed, you can expect three doubles. If you read the word car on a line, you can expect four doubles afterwards. So, and of course, you read those numbers, you can allocate the object accordingly. So this input file, again, is going to be using Linux redirection to read in this file. So each line pretty much makes sense what each line contains. Now the hard part is going to be to construct a binary tree from this. So you're going to have to do essentially a recursive function that's going to build your tree in pre-order fashion. So let's go ahead and just take a look I'm going to look at crane3.txt, and I'm going to show you how this would have to look on a visual for a binary tree. Okay, so here's our crane3.txt file, and I'll just kind of walk you through to help you visualize how you would build it, but this is the tree you would want to end up getting from this input file. So from the root position, the first thing you read is a joint 5 and 2. So we would first create this node right here, and it will be a bin tree node because it's a joint object. And then we read in the 5 and the 2, and the 5 and the 2 would have to get stored actually into these two nodes. So 5 would have to get stored here, and 2 has to get stored here. But the issue is, because we can't store 5 and 2 on the actual pointer, we have to kind of emulate this by storing the 5 and 2 into the left and right child nodes respectively. So I put the 5 over here that tells the parent node that the length of the arm that reached this child was 5, and the length that reached this child was 2. So we first read in those two values, 5 and 2, and we're going to simply store them locally in some variable. And now recursively, we're going to call this function. We have to create a recursive function to construct this tree in pre-order fashion. So the recursive function is now going to read the next line of inputs. I'll highlight this. It reads in the next line, and we're going to move down the left side. So this tree is not all. So for now, just imagine that we're building these trees. So the space pen that circles the nodes means that these are the actual nodes we've so far built. The rest of these haven't been built yet. They're just like shadow nodes for right now. So the next line of code, we read in the joint, and we're going to allocate this node and assign it to the left side of the parent. Allocate this bin tree node. Reading the value 4 and 4, and we're going to store these 4s and 4s into left and right children. We're going to store them later on. Not going to store them just yet because we haven't actually constructed the left and right children yet, but we're going to still read the 4 and the 4 and just store them into a temporary variable in the function body just for right now. And then we're going to eventually write them into the two children. So recursively, we go to the next line of code, and then we're going to now build this new node right there. And this new node is going to be a joint, and then we're going to read in the values 2 and 1. So we read in the word joint, we allocate the node. So far, we're kind of building this tree in a leftward fashion. So the first 3 lines, this is the first joint, our second joint, and our third joint. So we kind of read these in that pre-order fashion. Okay, so now we read in the joint in 2 and 1, so we allocate the node, and we read in 2 and 1, and we're going to store them locally in some variable. And now we're going to recursively call a function and pass in the left child, or we're going to sort of process the left child of this node right there. So now the next line of code, next line of input, is a bike. So we're going to now allocate this bike object. And since it's a bike, that means it has to be a leaf. So we're going to allocate the bike, read in 1.52.0, and we're going to simply allocate this node, and we're going to return back up to the parent. And the parent, its left pointer has to attach itself to this child. And somehow we have to attach it to it. And now that it's attached, we can now take this value 2 and write that into this node. Okay, so in pre-order fashion, we return back. So after we return back, we have to now resume and now read in our next line of input and recursively call a function on the right side. So we jump over here, and we're going to first allocate a node. And we see our next line of code contains GoPed. So this is going to be a leaf node. So read in the rest of the contents of that line, allocate the node, and return back up to the parent. And the parent has to attach its right pointer to that new node. So now we attached it. Now that we attached it, we can now store the value 1 into this leaf node. Then return, after that, we process this joint's left and right side, return back to the parent of that joint, and the parent is now going to attach its left pointer to the to this child joint. So it's kind of doing both pre and post order, because it's kind of building it in pre-order fashion, but then it's going to attach itself. We're going to link the parent to the two children in that post-order type of fashion. So when we return back to the parent has to then attach to the left and then to the right child. So now we return back up to the parent, and the parent now attach it to the left child. It will store the value 4 into this node's arm length. And now we return back. We have to now go to our next line of input, read that in, and then we have to allocate something to the right side. So of course, we allocate a node right here, and we determine that this line contains GoPed. So we know it's gonna be a leaf node. We read in GoPed, reading these numbers, allocate the GoPed object by passing in the correct values into the constructor, then return back up, and now the parent will then now catch this it'll catch that child pointer. So we return, one way to do this, you don't have to do it this way, but I always return pointers as my return type. So the parent can then catch the child pointer, so the child node. So now the parent now attached to the right side. We can now store 4 into that node, and now we are done with this joint, return up to the parent, and the parent will then catch, it will attach to the left side, and then we're going to store the value 5 into that node, which is the arm length. So now we read our next line of input, which will be a car. So what happens is we recursively call a function, and then we allocate the car object right here. And since it's a car, it's not going to be a leaf node. So now we're done. So we allocate, we read in the word car and read in these 4 values, allocate the car object, return, and the parent will now attach itself to that child. Now it's attached, I can of course store the value 2 into that node, into the so I can store this value 2 right here into this node. So the right this right child's arm will contain the value 2, so we know the arm length is 2, and arm length here is 5, and so forth. So, of course, the hard part is going to be to code this recursively, but that's sort of the idea. So we read in the input line by line, but we are sort of navigating this tree in pre-order fashion as we build. So we read in the joint, read in our next joint, read in our bike, return back, read in our GoPed, return back, read in our GoPed, return back, read in the car, return back. So it's up to you how you set up the recursive function, but it's going to be in that kind of fashion. So you could actually first allocate the left child first and then recursively go to that node and then continue. It's up to you how you want to do it. So that way, then your build tree function could be a void function in that case. So it's up to you, but again, I'll leave this kind of open for you to figure out, but that's sort of the idea. So let's go ahead and figure out how do we actually determine or how do we write the function that's going to determine if this structure is balanced torque-wise or not. Okay, so the recursive function to actually determine that this structure is balanced, it's rather going to be sort of like a post-order type traversal. So you first will have an R pointer that will point to the root node. And since it's not a leaf, the way you can tell is that if the left and right are both null, then it's definitely not a leaf node. So then you have to recursively call this function on the left and right side to get the weights of the left and right side, and then multiply them. So you multiply it to so this 5 value, for example, is stored in this r's left get weight function, or get arm length function, sorry. And then r arrow right, or r get right, and then get arm length returns 2. So we can, of course, easily retrieve the 2 arm lengths. We have to get the 2 weights first. So we recursively have to move down this side right there. Again, we can see that this is not a leaf node, so you have to keep on traversing. So you have to first call a function to get the weight on the left side first. So we jump down over here, and then we again we determine this is again not going to be a leaf node. So you have to again call the function on the left side, and now we hit a leaf. So at this point, we can just return this object's weight. So we can return literally r arrow get weight, and return some type of weight value back up to the calling function. So whatever I don't know what the actual weight is, but it returns some weight back to us. Okay, and then we have to recursively call on the right side, and we determine that it's also going to be a leaf node, so we can go ahead and just return r arrow get weight, and returns the weight back up to the parent. Okay, so now this node received the left and right side weight. So we take the left side weight, multiply it by 2, and we get this 2 by just simply for the parent node, we do r arrow get left arrow get arm length, it returns 2, and we use the recursive function's result back, and then see on the right side, and we compare them. If they're the same, then we just have to simply return the sum of these 2 nodes up the tree. And then the parent node does the exact same thing. We get the left side weight, then we do the right side, gets the weight, and then we multiply left side of weight with the left side arm, then right side weight, right side arm, compare them. If they match, then we just return the sum of the two side weights. So we return a sum. The recursive function returns the weight back to us, the left and right side. We call this recursive function on r left and r right, and return a sum of that up to its parent and so forth until we finally hit the root. Now, at some point, you may have a case where, okay, maybe the torques will be off. So if that's the case, we have to return some type of a special value up to the parent that tells the parent there was something unbalanced on the left or right side. If that special value is returned, then we can return that special value up to its parent automatically because we know something went wrong. So if that special value, maybe -1, I don't know, that might be a good value. If you return -1, that means, oh, wait a minute, something went wrong on that side. So let's say, for example, at this level right here. Let's say right here, at this level, the torques weren't matched. So I return -1 to the parent. This node receives -1 on the left side. If that's the case, I'm not even going to try the right side. I'm going to return -1 immediately up to the parent, and that -1 gets literally relayed up the tree immediately because each parent will receive -1, and that parent will get the trigger that says, oh, okay, something at the lower level went wrong, so this can't be balanced, so we're done. But if that -1's not returned, then we try to actually compute the torque of that side, and then compute the other side's weight, get that side's torque, compare them, and return the sum of the two children, or some of the two recursive function calls up to the parent. So again, I don't want to give out the code, but this is kind of a little bit of an idea of how to get started on this. So you also want to have another function to deallocate this tree, but deallocation should be pretty simple. I believe we have a virtual destructor set up. Actually, yeah, virtual destructor is set up for our class. And basically, we can just simply deallocate this tree in post-order fashion. So for every node, we first recursively call the deallocation on the left side, then the right side, and then we deallocate R. So it's just like the post-order traversal, except we don't see out the left. We don't see out R. We just we delete R. We deallocate that node. So that's actually not a big deal because I believe on CodeGrade at the moment, I don't know how to actually check for memory leaks. So we'll just kind of look at that and make sure you actually wrote that, but it's very simple. It's going to be almost the same code like the post-order traversal in class, except instead of cout R, you delete R. That's the only difference between, that's how you would write the allocate tree function. Okay, let me go ahead and just show you a quick run as to how to execute this program in terminal, and then we'll be done with the video. Okay, so before I continue with this, I just want to make a quick adjustment. So there is no virtual destructor in our bin tree node class because each node is not going to actually allocate anything dynamically, not the nodes internally themselves. So there's no virtual destructors, so don't worry about that. Okay, so now to run our program. So I provide you with the binary tree classes.h file. So all you have to do is write the main and then simply include that header file in your main. And of course, include other, other libraries as well, like for input and so forth. So to compile, all you'd have to do is g++ main.cpp, and then run this ./a.out, and then crane 01.txt. So again, we're going to use the Linux redirection. So we're going to essentially have cin will be redirected to read from this file. So just you can treat your cin like a file stream variable. So it will construct your structure. It should construct it, and it will go through and determine if everything is balanced. And again, we can also run this on our other input files provided. And then for crane 3, we get this output. So if it outputs crane can lift the items, everything is balanced, everything's fine. If it outputs, well, this is awkward, that means there was a problem. So which I guess, well, this is awkward would be the right output. I mean, imagine this was unbalanced and the crane tips over on its side. That would be actually much more than awkward, but we'll say for now, this is awkward. So you have to output this to the terminal. If it was unbalanced, and your output crane can lift the items. If it is balanced, and that's basically it. So hopefully this video did give you some help to get started. So I guess that's it for now, and happy coding.